Hi, and welcome to the second video in the series about implementing a C++ class for handling big integers. In the previous episode, I discussed the memory layout and decided to use std vector as the backend. I also set up constructors and assignment operators. Today, I'll be talking about the core of this project, namely arithmetic operations. But first, a few words about how I overloaded arithmetic operators, because there are many ways to do that. One could be tempted to write a bunch of overloads, but more does not mean better, as you can end up with ambiguity between overloads. I put all the actual code in operator plus equals, and operator plus calls operator plus equals. Note that it receives a reference to other to avoid copying. It is declared as const because you do not expect the other object to be modified during this operation. And it returns a pointer to itself, again, avoiding copying. On the other hand, the operator plus receives the first operand by value and the second operand by reference. The copy constructor is called to create a new copy of A, which is not const, and this allows to call operator plus equals on A. Also, we have to return A by value because otherwise we'll have a pointer to deallocated memory. The compiler will normally optimize this with RVO, return value optimization, meaning that the object will be stored in the caller's memory and no copy or move constructor will ever be called on return. Now, how do we add numbers? In this example, I have A, which is a 4-word number, and B has 3 words. Remember, memory addresses grow from right to left. I start by adding the least significant words, and then I go on towards the most significant ones. I can sum two 64-bit integers, but it may overflow. If it overflows, we must keep track of the carry. There are fundamentally 2 ways to address this in C++. The first way is to check if the carry flag has been set. Compilers provide what is called intrinsics, functions that translate into very specific CPU instructions. I could use those to access the carry flag rather than write inline assembly. And the second way is to use a larger data type that will prevent overflow. Modern compilers provide a software emulation of unsigned int 128, which translates into very similar machine code, which involves adding and checking carry flag. Last thing, in the resulting number, we may have another word appearing here in case the last addition overflows. Here you can see an implementation of the second method, that is with unsigned int 128. There are 2 consecutive loops, one from 0 to min size and the second from min size to max size. Their bodies are very similar, except that beyond min size, only one of the 2 numbers has limbs to sum, which needs different logic. In both loops, I first cast the body index I to int 128 so that all sums are done in 128 bits and do not overflow. Then the lower 64 bits are written back into body index I. And finally, the higher 64 bits become the carry for the next iteration. In this case, carry can be either 1 or 0. If after the last iteration carry is not 0, then I resize the array and write carry into the highest limb. I reflected quite a bit on the optimal way to resize the array. Assuming there are no leading 0 limbs, the result is either max size or max size plus 1 long, in case there is a carry. There are two strategies. Either I resize to max plus 1 since the beginning and shrink if needed in the end. The idea here is that shrinking is cheap because there is no memory reallocation. The second way is to resize to max, as I do here, and then add an extra limb only if needed in the end. This code, as you can see, implements the second variant. If the first operand is at least as long as the second, the first resize does nothing, and the second occurs only if there's a carry. Unless your data is very likely to overflow, I believe this could be more efficient, but let me know in the comments if you think otherwise. Now is probably the right time to talk about optimization, because you may be saying, oh, this code is not optimal. Let's do it with a cautionary statement. Do not optimize prematurely. There's a lot of benefit in writing clean, clear code and letting the compiler do the optimization. And you'll be surprised how good modern compilers are in optimizing. Do manual tweaks only if you're going after the ultimate efficiency. End of cautionary statement. I have already tried 2 alternative methods, and that's why you see these preprocessor directives here. Let me show you the use of intrinsics first. The algorithm is exactly the same, but code is actually much shorter and neater. This function, built-in addCLL, is specially designed for what we are trying to achieve here, as it sums the first 2 operands, considering the carry in, and it outputs the carry out. The whole calculation becomes a one-liner. The other function here does the same thing, but without taking the carry in. Bear in mind that these are not part of the C++ standard, but all modern compilers have those. I like this code for its compactness, but does it improve the runtime? Barely. My test procedure runs an addition with operator plus equals 10 million times, and it does 100 trials for averaging. The runtime is about 10% down, which is somewhat underwhelming. Let's investigate why. Digging into the disassembly of the original code with int 128, compiled with maximum optimization, I realized that Clang did not actually use 120-bit arithmetic. Instead, it performed a 2-stage carry, which actually happens here. The first operation, add s, adds a with the carry in and sets the carry flag. cset stores the carry flag in register W12, which is the lower part of X12. Then another add s adds b and sets the carry flag. And finally, the fourth instruction increments register X8 only if the carry is set in the second addition. So this was already pretty optimal. And code generated with intrinsics is very similar. Okay, it was a nice try, and kudos to Clang for recognizing the pattern. Really impressive. I also wanted to try another idea. Rewrite the loops using iterators. The idea here was to get rid of the counter variable I and iterate with what boils down to pointer arithmetic. Indeed, iterators for std vector are basically raw pointers. So, does it improve the runtime? No. For full disclosure, when I was running only one trial, I had very similar runtime for the three. I don't really understand why it degrades significantly when running multiple trials. But anyway, it does not improve runtime. My guess is that you lose efficiency because you need two iterators, one for each vector, testing for both, and a bunch of helper variables. So in the end, the code is neither clean nor efficient. So the original int 128 version was not so bad after all. Going back to the assembly that I showed earlier, it's quite clean. You notice that the first loop for some reason transformed into a countdown loop, but not the second one. And the instruction that stores the value in the array also advances the pointer by 8 bytes in one single operation, and the same works for loading. This is proof that micro-optimizations will not radically speed up your code. What you should do instead is to make sure that you are not missing something big. Here's an example. I run the same test, but instead of a plus equals b, I do a equals a plus b. Now it takes 10 times longer. Why? Because operator plus calls a copy constructor which allocates memory on the heap. This operation is expensive. So the real big optimization is to use plus equals, and if possible, have the longer operand on the left. This makes me think that I should be doing less trimming, but that's a topic for another day. Stay tuned for the next episode, and thanks for watching.